This is Mirabilis Design's webinar on hardware-software partitioning in SoCs based on power, performance, and functionality. When you look at your design challenges in architecting a system, the partitioning between hardware and software is probably the most relevant. The elements of hardware and software partitioning that you're looking at would be to first get an accurate representation of your system on chip by incorporating the functionality, timing, and the associated power management or the power algorithms, and be able to generate a variety of profiles. So profiles can be based on power based or it can be based on timing based, and really work in a collaborative manner by incorporating the interests or the requirements from your firmware designers, marketing, the systems team, and possibly your customers as well. The purpose of doing that is to really select the right IPs and the right topology based on the use cases that your system will be going through. Once you get such an architecture, you want to be able to have a mechanism to be able to feed the requirement data and feed in the traces to the downstream implementation so that they have accurate representation or an accurate specification that they can use during their development. A quick introduction to Mirabilis Design. We've been around since 2003. We're based in Sunnyvale, California, and we're experts in modeling and simulation at the system level. We've got over 50 customers worldwide. The modeling and simulation environment is called VisualSim. And the purpose is to really get a complete understanding, a very clear understanding, and be able to do the optimization of your specification prior to any development. So this can incorporate software partitioning, power analysis, sizing the system, figuring out the topology, all of those kind of attributes. The goal is to get the right configuration to match the customer's request. The product is called VisualSim Architect. And in VisualSim, what is unique is that it really incorporates your entire system or SoC. So it incorporates your hardware, your software, and your network. So your hardware could be your GPU, your processors, your DSPs, hardware accelerators, DMAs, any of those. Your software can be the application, the firmware, the schedulers, and of course, the network can be any of the buses, the interfaces, the IOs, crossbars, any of those aspects. Now, when you look at performance, what you're really thinking about is timing analysis, like, what is my latencies, the amount of effective throughput or quality of service I'm getting. Power is looking at your instant and your peak and your average and cumulative power, either at a per IP level or for the entire chip. Then comes hardware-software partitioning, which is the main purpose of our design today or our webinar today, which is really about looking at how I can quickly determine what are the functions or elements of my design that need to be moved over to hardware so that I can free up my core processors to be doing all the other tasks that it needs to do, all the special, like the more general purpose tasks and things like that. That way, I can either reduce the power or improve performance of my system. The other piece of VisualSim is that underlying is a discrete event simulator, so everything runs on events. And we have analysis tools and interfaces to a variety of other environments so that you continue to use your current design domain tools for your downstream implementation as well. Again, if anyone has any questions, please enter them in the chat window and we'll either incorporate it in the presentation or we will later on respond to you as well through either email or through some of the web chat opportunities. One of the key things about VisualSim is really looking at collaborative engineering. How can I extend the role of system engineering to go beyond to incorporate partners, customers, firmware groups, systems groups, things like that. And the way to do that is to be able to take the models and make it available to everybody else that's in the product development chain. Now, one of the things I'm going to do right now is I'm going to show you a quick demo of how VisualSim is actually being carried over beyond the development environment that you're familiar with. So we're going to take up a design of this kind, which is it's got two buses, a bridge, a CPU, and it has two CPUs. It's got a DSP, and it's got an I/O device as well. Now, what you see here are the use cases associated with with this particular system. So you have your architecture and you have your applications. We've got two concurrent applications, albeit each of them runs at different rates. This one, for example, is this one here, for example, is running at 1.7 E6, so which is about every every half a microsecond you're getting some data out. This one is running at a slightly different rate as well. What I can do from here is I'm going to launch this and bring this up right from within the browser. Why do we do this? The purpose is that once you've built a model, you can run your simulation analysis right over here. So this is from the browser, and I can go ahead and click on the Go button, and you can see a variety of statistics. So for example, this is your the latency for completing your software task from the time it started to the time it completed. It shows you that information. Now what I can do is I can change the clock speeds of this model. So both of these, I'm going to change them to 400 megahertz. And you can see how much the difference. We were at 1.5 microseconds. We've dropped to close to 1 microsecond. So by varying the system attributes, you can see what the performance of your system is. So this is what VisualSim allows you to experiment or try out in your development or your design process, and be able to collaboratively do it with other members of your team. Now, a quick introduction. VisualSim has a large library of components that you can use to quickly assemble a system. All of these are at a level of accuracy where you can get things like your timing information, like response times, read-write latencies, things like on the process you can get like hit-miss ratios. On memories you can see which device made how many requests and what was the total throughput you need to get out of the memory, so you can size your memory devices, things like that. Now, why do you need to do discrete event simulations and be able to do detailed analysis at the system level before you start your RTL? One of the complaints is that, yep, it takes way too much time. I shouldn't really be trying out. But the problem really is, in this particular case, if you look at this very traditional way of doing power analysis, you list out all your devices, you create a Excel spreadsheet where you put in the power of each device, and either you take the average of it or you take the worst case. You add up all of them. In this case, we're taking the average, and we end up right over here, exactly over here. But then in reality, each of these devices could be at a different state. So if you take just the active for all of it all the time, you're creating a requirement that's way too high. If you take an average like this, you're finding out that for certain use cases, the power can be much higher. So this is where the activity-based power and timing analysis comes into play. It's because when you start getting a more accurate representation before you do your development, much easier and much faster to do hardware-software partitioning. Now, what are the types of explorations you do to come up with the hardware-software partitioning? The first one is you have new concepts. So, for example, I could be building up a different type of a bus, or I can be trying a different type of a hardware accelerator. The other piece of it is I can look at the feasibility of the system, or maybe change the topologies. I can have different types of workloads and use cases. And I can try out different power rates associated with different clock speeds. Now, let's look at the system model. So what do we have? We have three parts to the system. The first part is your hardware architecture. The second part is your behavior. And the third part is the data associated with some of the static details of your system. When you run the simulation, the output gives you a variety of statistics like power, utilization, the latencies, things like that. So now what I'm going to do is move from here to an actual model that runs in VisualSim. So this is a block diagram. I've got an ARM-based architecture right over here. So what I'm going to do is just open up this window right over here and look into this hierarchical block where you see an ARM9, a milk coprocessor, some buses, caches, AXI buses with bridges, and external connected out to the external world as well. So this is your main chip, and that's a memory controller that's connected to the DRAM and flashes. Now, I also have a hardware accelerator, which initially the whole design, which is in this case a multimedia SoC, the whole design is running purely in hardware, I mean software. So which means they're all implemented on the processor. So I'm not actually doing any hardware accelerator. Now, how do I make decision on which hardware accelerator or which components are required for hardware accelerator? There's a few things that you can make decisions based on. One of the things is looking at the detailed statistics to see who is consuming how much of the resources. That is one way to do it. The other way to do it is looking at my peak power consumption. How much power is being consumed overall in my system. So you can see most of the time it's down here, but then you can see the spike is fairly high here, like 0.95 watts. But you see a spike to 1.35 watts, which is almost 40% over the standard norms. Now, what is our goal in this model? The hardware software partitioning, the goal, I need to get to about 13,000 frames in 20 milliseconds. And I need to, the power must be less than 2 watts of power. I'm sorry, 1 watt of power. So you see over here, we're at 6,600, which is far less than half of our requirement. But the power is good. It's less than 1 watt. So what do we do next? Let's look at, based on the statistics I showed you, we can look at, which of these can be moved to hardware. So one of the ones we picked up was this one here, based on the statistics I showed you. And so what we're going to do is, rather than running this on software, we're going to change this to run on the hardware accelerator. Same model, initially we're running software. We found the performance was not good, power was okay, but now what we're going to do is incorporate a hardware accelerator into the exact same design. So now when we do that, what you see now is a variation of the same design, but you suddenly notice the power shot up. It's no longer 1.35 as the peak, 0.95 to 1.35. We're actually hitting over 1.9. So we were over here at the peak, now we're at 1.9. Huge jump. Why is that? Because you see, when we incorporated the hardware engine or the accelerator, it stays high right through the system. The good news is we went over 14,000 frames, but bad news is we went over 1.5 watts of power, where we only allowed to have about 1 watt of power. So what do we do? The next step is, we know from the design that the hardware engine is the one that's consuming most of the power here. So what we'll do is, we will take the same design, but go into our power table and incorporate a power management logic. So we'll incorporate that here. And what we're going to do here is, we're saying as soon as this hardware engine goes into standby mode, push him down to idle within 1 nanosecond. Exact same model we did, first moved from software to hardware to get the performance. We got that, still missing power. So what we do is we move the hardware accelerator into a extreme power management to try to see how that impacts our power and performance. So now we go ahead and run it. Look at this. It didn't stop at the 1.35, it actually still went up, but earlier on it was at 1.99. We got it down to the peaks to about 1.65. So definitely an improvement. But then notice here, we're dropping it down as much as possible. So what's happening here? We got the power to less than 1 watt of power, and we still have the performance over 13,000. And also notice it's not as high anymore. So what has happened now is, through my analysis, we're able to determine what is the hardware software partitioning, but at the same time looking at ways how I can keep my power down below a threshold. Allows me to do that. Now the next question comes up is, hey, I still have these spikes. How can I eliminate these spikes so that my system still continues to run at the performance that I want, but I'm getting the I'm getting the power to be at a much more in a much better range. So one of the things you can do in VisualSim is you can do what's called dynamic voltage frequency scaling. So let's take a simple design here. We've got 4 concurrent tasks that are hitting a multi-core where we've got 4 cores. Now we assume that all the cores are identical. So we're setting up these cores with a fixed power, with a fixed clock speed. And we're going ahead and running the simulations. So you can actually see right over here the all the 4 cores are being used. The maximum power is about 1 watt of power, but the average is less than 0.2 watts. Now, what do we do different? What we're going to try to do is, now all of these are occurring as you saw at the exact same time. Now, what we're going to change into the model is, rather than having them occur at the same time, we're going to do some offsetting of some of these software tasks. They're not occurring exactly at the same time. So we're going to offset each of these tasks by 3.5 milliseconds. Exact same design, no change to hardware. We moved to hardware we got hardware accelerators. We got the multi-core where we originally had a single core. We're trying on multi-core, same design. And now what we're going to do is we have created an offset so the software is not arriving at the same time. So what happened? We went from about 1 watt of power, 1 milliwatt of power to about half a milliwatt of power. Notice the average didn't really change all that much. It's still about very close to the same number. But then the peak power dropped off because we're able to offset these substantially. So as a result of doing that, we're actually able to improve the power performance of our system. So we got our hardware accelerators figured out. Now, once we got the hardware accelerators figured out, now we're also able to figure out what the performance is going to be in terms of looking at ways how we can modify the software task execution and the hardware accelerator execution, especially with regards to going and accessing memories and things like that, which is where most of the power is being consumed. So in this case, we were able to actually modify the the offset of the software task so we can further reduce the power. Now, the next step is, why not try to make the clock speed a little more dynamic? So what we have over here is we say, let's randomly make it between 100 and 800 megahertz. So the idea is that, if for different clock speeds, how does my software task? I still have it offsetted, but now I'm dynamically changing the power, the clock speeds. Unfortunately, I made it a little too dynamic, so it actually went all over the place. So now we're actually seeing what used to be less than 1 watt of power. We're actually shooting it up to about 1 milliwatt of power. We're shooting it up to about 25 milliwatts of power as a result of having an over-designed system. So earlier on, we had a system that was highly under-designed, now or well-designed, and now we have a system that's highly over-designed. As you can see, the response time has dropped off quite a bit, but then the power consumption has peaked a lot. So when you look at these architecture exploration, you can look at ways how I can do hardware software partitioning, but do it in a way where we can incorporate the power and performance within the same architecture model. Again, if you have any questions, please bring them up right now. I'll try to incorporate in a presentation or have someone respond to you. So looking back at that model that we constructed, as I'd mentioned, we had 3 parts to the model. The first part was the architecture, which is your hardware and software platform. Remember, I just showed you only the hardware thing of the processors, the buses, the memories, the caches, but you can also incorporate like runtime environments, schedulers, operating systems, things like that as well. The behavior flow is the actual use case That's going to be running on the system. In this case, it's a multimedia application. It could be something else in other designs. And below here is some of the attributes of the system. In this particular case, the spreadsheet is the power, but it can be other performance attributes. It can be the mapping of each function to a multi-core architecture, things like that as well. Now, one of the key things in any design is looking at the hardware software related to memory access, because your read-write latency has a huge impact on your performance of your system. So even if your pipeline does very well in terms of execution, your read-write latency can cause a huge disruption or huge slowdown in your actual application behavior. So one of the things you can do is you can set up these different elements, have hierarchical buses. It can be a network on chip, could be an AXI, could be any of those. And you connect them into, say, multiple memories. And each memory can have its own number of banks. And you can have any number of banks. And oh, here we go. You can see the bitmap has got, in this case, 3 bits, so it's got 8 banks each. Now, when we run such a model, you can see what the power is consuming from all those different devices. So the blue is your instantaneous, the red is the average. Now this one here is more important. This one's showing you all your activate related power, which is your your RPs and RAS and things like that. This is the actual write operation. Well, this is your refresh. So you're kind of splitting up your power into these 3 subcomponents where you can actually evaluate how I do my partitioning based on my power consumption. Now, a quick step back. There's always a concern that your system design tends to be very inaccurate at the system level. Now, if you had, say, a network on chip that looked like this with individual components connected to it, you would, in VisualSim, each of these would represent a node with certain routing and some delays or things like that. Now, each one of these represents this full system. How is the system design model different from a signal level model? The similarities, of course, you have all your clock speeds, your widths, your buffers, your algorithms, your logic, things like that. Only thing is that we use a data structure which actually combines your data and your control and any other simulation related attributes into the same data structure that flows through. The main difference is that you don't have to define all those address translations, your pin definitions, your signal handshaking, though you still incorporate the timing into the model. Because a lot of times when you're writing your RTL code, a lot of it is related to protocol conversions and things like that don't really impact your performance, don't really impact your power. So those things are skipped. So when you do that, and also, even though we run clock by clock, we don't have to incorporate the clocks that are not doing anything. You can still incorporate the power and performance as delays for that time period, but you don't actually incorporate the actual clock itself for those events. So as a result of that, you can get up to 1000x faster performance than any of the other mechanisms that you might use for system modeling. Now, let's step back and look at VisualSim and see how the modeling actually takes place in VisualSim. In VisualSim, there's actually 3 levels of modeling. There is the first level, which can be called a functional or untimed model, where you're looking at what's your flows, what's your hierarchy of flows. There might be some simple delays, buffers, and the sequence of tasks that are going to be executed. Now, these would help you look at future technologies, look at how I should implement certain attributes of my system. The next one is looking at more, I'm going to buy off-the-shelf IP blocks, put them all together, like processors, GPUs, memories, etc. And I want to see whether it meets my requirement. The third one is really what we call custom and cycle accurate, which is a combination of 1 and 2, which is some of them are standard IP blocks, some of them I'm building custom, some of them I'm incorporating someone's IP block, but then I'm writing my own arbitration. So we've got a scripting language that allows you to assemble up this type of a system. So when I look at the design over here, and I open up this block, It's a full off-the-shelf component. We're just incorporating all of them. But here I have a hardware accelerator that's completely custom. And I have a bus here where I can incorporate more of a custom arbitration file. So in this model, it's actually a combination of 1, 2, and 3 to incorporate the system. Now, when I look at the power, I actually see my power table over here, and I can actually have different types of expressions for my power management algorithm as well. So allows me to incorporate all three into a single model. Now, let's take a step back and look at VisualSim and try to understand why do we have different parts of the system. Obviously, the libraries are here so that you can assemble up your full design rather than having to try to build each component. And even if you build custom components, you can put that into the library. The other part is your parameters. One of the things with graphical modeling is to help you understand the system, debug it, visualize what's happening in your design, use it for presentation. But once you're happy with your model, you may want to run thousands of simulations. That's where the parameter sweep comes into existence. And the parameter sweep allows you to be able to create what's called a command line or a batch mode simulation through script, and then just run thousands of simulations concurrently. You don't do that from the GUI, you do that from the command line, and you run off simulations. Apart from that, we have resource modeling, which is more on the hardware side. You have statistics that you can set up. You have a variety of workloads. They can be synthetic workloads, which are more distribution-based, or trace, which is like a file reader that you can actually incorporate them into the model. Some of them run at close to about 100,000 lines per second, so they're extremely fast. The VisualSim simulator itself runs at about 1.2 million activities per second, so it's like extremely fast design. Now, if you take the concept of power, so one of the things that most people do with power today is really look at power as an afterthought, where I'm just saying, okay, I'm doing this function, so there's a delay, I'm doing this function as a delay. What VisualSim does is take it to the next level, which is look at it as activity-based and state-based power analysis, which is at any instance of time, each device is in a different state or it's moving into a change of state. In addition to that, on an overlay, there's the power management logic, which can make a change to a state either because it's been idling in a specific state or because the power, the battery is low on power charge, so it needs to be moved to a lower state. So really, power is an integral part of your hardware-software partitioning design. Now, when you look at your system, you can have a variety of applications or designs. So they can be routers, switches, storage, any kind of a system. And what you want to do is you really want to increase your battery life and be able to use enhance your network bandwidth usage, which is, if I have, say, a IoT device that I'm building my SoC around, I might need an RF system that, and I'm just going to open up. A design right here, so you can so what I have over here is I'm using my chip and I'm creating an IoT device, and I've got a network of these IoT devices that are connected to hubs locally, which goes across the internet to get to a data center, which has a series of servers that are there. And what I want to do is try to understand if I change the data sizes over here, change the amount of requests that turns on and turns off the low energy Bluetooth, how does the power consumption change? So what I have over here, when I open up this thing, this is a process called hierarchical modeling. When I open up this block over here, you actually see what is different here, which is, I've got a battery, I've got an energy harvester, which is part of my IoT device. But here I've got AFEs, I've got MCUs, radio transceivers, and right here I have the BLE core. And when I go dive down deeper into it, I finally see that I've got a finite state machine at the bottom that's actually describing the activities associated with this Bluetooth core. Okay. So what this allows you to do is allows you to model not just your single chip, but also model the entire system that the chip would be incorporated into. Why is that important? Because I might want to see how I can modify the chip's behavior based on the power, based on how much power is being consumed, or what is the response time it takes on the network, things like that. So I can tune the variables of my system for that. And that's the IoT device that you just saw right now. And we're using a variety of building blocks out of the library to actually assemble this, except for the Bluetooth core, which had its own state machine for the algorithm. Everything else was picked up from off-the-shelf components. Now, when you look at the reports, you can see what's the MIPS on each of the devices. And you can see what the latency for each of the devices were. You notice right over here, notice there are some differences in the latency for each. Why? Because the data sizes could be different. The applications that might be utilizing it might be different, because some might be uploading some data, some might be downloading data, some might be just doing updates. So it could be a variety of things. The key aspect is really this one over here, the tracing. So one of the things that a model allows you to do is allows you to see if the sequence of things that it has been executing is done correctly. If it is done correctly, then you know that your system is also behaving accurately. So you can also see in this particular case, what's the network path that the system took to go, from end to end for accessing the data center. You can actually see how the performance changes if the network configuration change and things like that. Now, same thing at the network level or at the RF level, we'll look at the storage level. So you can actually look for different sizes, for different speeds, for different bus widths and things like that. What is the performance? So here I'm comparing flash versus HDD in terms of what is the latency plot and what's the power consumption plot. And you can see what the difference is between the two architectures as well, both in terms of the average and in terms of the instantaneous power for this particular application. Now, if you notice over here, this is 10 to the power minus 4, 10 to the power minus 3. So this one actually takes about a 10 times more latency relative to the flash, for everything else being the same. Now, also this consumes about almost about 10% more power relative to the flash as well. So all around, the flash is better than the HDD. Unfortunately, flash costs more, so you have to look at the price also to incorporate that into your design analysis. Now, one of the things with VisualSim to help understand how the system behaves is really looking at the infrastructure that VisualSim resides in. So one of the things that VisualSim resides in is an environment where you can actually run VisualSim across multiple operating systems, and it has an underlying XML database. So each person can create their own components, put them into a central database, and everybody would view those databases right in their library on the left-hand side, is because it already exists right there. And these are called class libraries that you set up these systems. Now, one of the other things of VisualSim is we have actually created an environment which requires very little memory consumption. As a result of having very little memory usage, you can actually run extremely large models. Like in the case of a complete SoC can be run within our environment and can be even simulated. As you saw, we had a full SoC that was about 20 milliseconds of simulation, took only about 10 or 12 seconds to complete. So it can run extremely fast. The other aspect is trying to incorporate traces from existing designs, use a CSV file for actually making topology or even even like parameter changes to your system. The other aspect is command line simulation. So once you're done and happy with your model, you can actually run simulations right from the command line. You can run it extremely fast. Now, what do you do once you're done with the VisualSim model? Once a VisualSim model is done or it's built up, it really becomes a rapid prototyping platform to look at project feasibility or new ideas. The other one is that when you do these platforms, you can actually combine timing, power, and functionality to do your hardware software partitioning. And also when you incorporate a hardware software partitioning, you can also try to modify your firmware and see how that impacts your overall performance. Now, what you can also do is you can create traces like power state traces or start time, end time schedule of your tasks and feed that to your implementation team so that they can use it for their assertions or for their verification process as well. Now, the web-based interface allows you to be able to communicate and collaborate with the rest of your team, either internally to the company or external as well. So with this, I want to thank you for attending this presentation of VisualSim's webinar on hardware software partitioning in SoCs. If you have any questions, I can answer them right now. You can feel free to send an email and we can chat at that time as well.